flux is flux. Imagine you're a bouncer on the door of a venue and you need to know how many people are entering and how many are leaving. So you have a counter in your hand and you click up when somebody enters and you click down when somebody leaves. So that, the number on the counter, is your flux. A guy named Carl Gauss realised that this could be applied to electric fields and magnetic fields. So in this case our people would be our field and the route that the people take would be our field lines. And then the counter, the flux, is the number of people, or field lines, that are entering or leaving. A guy named Carl Gauss realised this principle could be applied to electrical and magnetic fields. Around the turn of the 19th century, we knew about electricity and we knew about magnetism, but we didn't have much by way of a theory unifying the two. Maxwell was about to change that. Back when he was young and beardless, Maxwell was still a pretty smart guy. When he was just 14, he wrote a paper showing a way to measure the motion of light. And sometime later, a German mathematician named Carl Gauss had been working on a way to capture the behaviour of electric and magnetic fields. That's our flux counter from earlier. And Maxwell realised he could use this to explain the way the two interacted. So on New Year's Day in 1865, he published his paper on the subject, and bam! Instant beard. Then, in the finest scientific tradition, Oliver Heaviside and Heinrich Hertz simplified Maxwell's original 20 equations into 4. They were in awe of Maxwell's glorious beardage, so the equations kept Maxwell's name. One of the key things that separates electric fields from magnetic fields is the idea that there are no magnetic monopoles. What that means is every magnet, no matter its size or shape, always has a north and south pole. The classic iron filings experiment shows us this in action. You can see that the filings follow an invisible loop from one side of the magnet to the other, and as you saw, the original red and blue magnet was a bit weak, so we swapped it to a stronger one. Gauss's law, as it came to be known, claims that the net magnetic flux through a closed surface is zero. So if you imagine that the surface of our magnet here is our venue, then basically the venue is banging and every person who leaves comes back again, and your counter always reads zero. But are there no magnetic monopoles? In order to establish Okay, I'll do it. As you can see, the magnet, now cut in half, has two distinct magnetic fields. There's a clear separation in the middle, and as the magnet is returned to its original state, we see the field return to normal. This is pretty good experimental evidence that Gauss and Maxwell were right. Here is the full bells and whistles equation in its integral and differential forms. Looking at the integral form, the left-hand side is our magnetic flux and, as we've just discovered, that equals 0 over a closed surface. So the circle and the letter S indicate that the integral is over that closed surface. The B is our magnetic field, and the N with a little hat on it is a vector normal or perpendicular to the surface. We want those to point in the same direction to make our calculations easier. The final part, the dA, is a small section of the area of our surface that we're looking to integrate over. The second form, the differential form, tells us that the divergence of the magnetic field is 0. And these two things are equivalent, they just use different methods to solve them. So there you have it, Gauss's law for magnetism. I'm afraid I no longer have time to show you how to actually integrate it in a real world scenario, but it's been real. Peace out.